Hello everyone. In this lecture video, I am going to tell you how to represent floating point numbers or what is floating point numbers. This number representation follows a standard given by Institute of Electrical and Electronics Engineering, and the name of the standard is IEEE 754 for single precision number representation and the same for double precision number representation. I have started this number representation, base conversion, sign and magnitude, and two's complement number representation in my previous video. So if you haven't gone through them, please go through them. And today particularly I will show you what is floating point number representation. We needed the required foundation to come to this point. So if you haven't got the number representation foundation before, please go through those videos also. Now, in a computer system, various codes are used. The codes are like systematic use of a given set of symbol to represent some information. Like from a daily life example, I can talk about the traffic light signaling system, where red light is used to stop the traffic, yellow light for caution, and green light for go. So similarly, the number representation system follows the codes or a systematic use of information. So far we have seen fixed point number representation, where a number will have the integer part, then the radix point, then the fraction part. And as the number is represented with a number of bits or the data word, so how many bits will be before the radix point will be fixed there, and how many bits will be used to represent the fraction is fixed there. And in that number representation system, there is some drawback or limitation. In fixed point numbers, you can only represent a finite range of numbers, which is less than what floating point number can represent. So floating point number will represent a bigger range of number, and the precision of any measurement we can express in more detail or more precisely in floating point number representation. So as a foundation for fixed number representation, previously I have gone through that those numbers are represented as a sign and magnitude number, or as a two's complement number or one's complement number, and where the integer will be represented with a sign bit. Uh, 1 is for negative number, 0 is for positive number, and then the magnitude part in binary or in hexadecimal anyways. And then for integer, the radix point is implied. It is at the end to the right hand side. And we usually don't use that radix point because it is the integer and there is no fraction part. And for fraction, we use the sign bit and then the implied radix point. We usually write 0 point and then the magnitude of the fraction. That's the way we represent a fixed point number. Now we are going to see what is floating point number and how it can be represented following that IEEE 754 standard. So for representing floating point number, like n is the number, n is m times r to the power e, where m is the mantissa or the magnitude, r is the base of the numbering system, either binary or decimal or hexadecimal, any base you are using, and capital E is the exponent part. So same number we can represent like this, m divided by r, because we are dividing by 1 r, we will be adding that here. r to the power e plus 1. Or we can represent it like this: m times r multiplied by r to the power e minus 1. So as a practical example, if m is my number, a binary base number 1101.0101, so this number I am representing by moving the binary point in front of all digit, and because I am moving it towards the left 4 bits, I am multiplying it by 2 to the power 4, because you know each location, each position has a weight of 2. Here it is 2 to the power 0, 2 to the power 1, 2 squared 2 cube. Because the binary point is moved to the front, it became a fraction, so you have to multiply it by 2 to the power 4. Same number you can represent it like this: 0, 1, 1, adding one extra 0, so here the exponent is also increasing by 1. Or you can add two zeros in front of the number, and here you are writing it as 2 to the power 6. So if you are writing in so many different ways, that means the data word required uh, for this representation, the third one, is more. Or if the data word is still the same, then you are losing the least significant bits. You have to ignore them, because you cannot accommodate all the bits in that particular limited data width. So for floating point number, a standard method is used, that is called normalization of the number, and it is assumed that normalization is used for a unique representation. Mantissa has a non-zero value in its most significant digit position. So this is not a normal representation. This is non, but this one is a normalized representation, because it is point. If I consider it is most significant digit, then this is a normal representation. So before going into the how to represent the exponent of the floating point number, we also have to see some other coding method, and that is called excess or biased representation. You must be all knowing the 2's complement number representation. I have also gone through the 2's complement number in my previous video on number system. So there you have seen that if the bit pattern is 0000, in 2's complement number system it is 0, and this particular number 0100 is equivalent to 4, and 1000, when it is starting with a leading 1, these numbers are all negative numbers, like 1000 is minus 8, and the last one 1110 is minus 2, like this. So all four ones, 1111, will be minus 1. So that was the 2's complement representation. Now, if we want to use excess 8 code, then with every number, 2's complement number, if you add 8, 8 is equivalent to 1000 in binary. So you will get a excess 8 representation. So if you add with 0, 1000, you are getting this, right? So it is equivalent to minus 8. So in excess 8 representation, all zeros minus 8, because minus 8 plus 8, you will get all zeros. So this is minus 8, and 0100 is minus 4, and it is like this. So here you learned a new thing, what is excess or bias representation, and it is actually applied on a 2's complement number, and that excess can be anything, excess 16 or excess 128, etc. Now, floating point number, n is the number m times r to the power e, where m is the mantissa, or called the significant, is a significant, and it has significant digits of m. And e is the exponent, is an integer exponent. This exponent is integer. And we can write the number n like this, right? Positional notation. It can be a positive or negative number. And then this is the radix point. From here, a0, a1, it goes up to a n minus 1 subscript. And in the fraction part, it goes from a minus 1 to up to a minus m. So in this representation, total n plus m bits are used, okay, to represent this real number. This much is used. Now, for a floating point number representation, we can move this point, this radix point in the front. So now you are getting this an minus 1, then it will, then at the last it is a minus m. All n plus m bits are here after the radix point, and then you are saying it is multiplied by r to the power n. Because you moved the binary point or the radix point in bits, you have to multiply it. The exponent will become n, r to the power n. So m is usually represented in sign and magnitude, the m part. This is the m part and this is the exponent part. So m will have a sign and magnitude, sign bit 0 for positive, 1 for negative, then point, and then this is the mantissa, and it is called radix and sign and magnitude representation of the mantissa. So this thing represents the magnitude and SM represents the sign bit. Okay. Now the exponent will be some excess k representation. So E is usually coded in excess k 2's complement. K is also called a bias. And what is the K? K is usually how many bits for K? So K is selected to be 2 to the power E minus 1, where E is the number of bits to represent the exponent. Okay, you are getting it? So if it is 8 bits for keeping the exponent part, so it will be 2 to the power 7, right? So 128 will be added with the exponent. So this E will range, then E will range from minus 2 to E minus 1, minus 2 to the power E minus 1 to 2 E minus 1 minus 1. So this you have seen, no, in 2's complement number, what is the range of number it can be represented. Suppose there are 4 bits I am using to represent a number in 2's complement number system. Then the it will range from 0 to 0 to minus 8, right? 0 to minus 8 will be the range. Or it will range from 7. 7 is the maximum positive number you can represent, and minus 8 will be the minimum number that can be represented. So similarly here also it is the same. So excess k form of E is written like this. It is the bias E minus 1 bit, then bias E minus 2 bit. Like this, it will range from 0 to E minus 1, means you are using E number of bits to represent the exponent. So combining all the part together, the sign and magnitude part, then the actual mantissa, then after the sign and magnitude, you actually keep the exponent part, and then at the last, you keep the mantissa part. So this is the full representation of the floating point number. So sign bit, then this many E number of exponent bit, and then N plus M mantissa bit. So this number will be -1 to the power sm. If it is negative, -1 to the power 1 is a negative. If it is a positive number, it will become plus here. -1 to the power 0 is +1. And then this was the mantissa in the fraction part of the mantissa. And then this is the exponent r to the power. This is the bias. This is the exponent with bias, and now you are minusing the bias part because you added to 2 to the power e minus 1 as a bias. Okay, so this will be the actual number that you have represented as a floating point number representation here. So if I give you an example, it will be clear. And before that, again, it is shown pictorially how where the bits are kept. First, the sign bits of the mantissa is kept. Then these bits are for the exponent e, and then the last bits are for the mantissa m. This is the floating point number format. Now let's see if this is a number, real number given in binary based system, how it will be represented as a floating point number. And here it is saying that for mantissa you have n plus m, total 10 bits, and for exponent you have 5 bits. So 10 plus 5 plus for sign, you can have the data with this 16 bits of data. So you tell me how to represent it as a floating point number. So first of all, you will be moving the binary point at the front. So it is becoming like this. Now see, in the fraction part, there are only 9 bits, but representation is for 10 bits. So you will just add 1 0 at the last. It's not going to change the value of the fraction, but you are utilizing all 10 bits. Okay. So this is the number as two binary number as sign and magnitude. This is the number. And now exponent was 2 to the power 6. 6 is the exponent. Okay. So 6 is given as a decimal number. First you convert it in a binary. 0 1 1 0 in binary is equivalent to 6. But to represent the exponent you have 5 bits, so you are adding another 0 in front. So it is 0 0 1 1 0. So it is binary number and a binary number to two's complement number system. Okay, so exponent is a two's complement number system, and mantissa is just a sign and magnitude binary system. Remember, these are different. This is sign and magnitude for mantissa, and because it is plus 6, no, this is in two's complement number system. It is like this. And now suppose you are adding, here it is said that to represent the number, add excess 16 to the 2's complement. So this was the number 6 plus you are adding 16. 16 is 10000, so it is becoming 10110. So this is the exponent in excess 16. So combining everything, here is the sign bit, then 5 bits of exponent and 10 bits of mantissa. So this will be the floating point number representation. This is not the IEEE standard. In our computer nowadays, we are using 32 bits number system. In old computer now we are using 64 bits. So IEEE 754 standard was given in 1985 as a 32-bit single precision number system, and then in 2008 they changed also, they incorporated also the double precision 64-bit number system. And this standard was developed in response to divergence of representation. All computer vendors should use the same number representation system so that they can process the data with the same amount of precision. And that's why this corporation, IEEE, they devise this standard for the number representation, the real number representation. So now see, we know that there are two formats. One is for single precision and another is for double precision. For single precision, total data width is 32 bits, and for double precision, total data width is 64 bits. Out of that, first bit is signed for both, and then exponent part for single precision is 8 bits, and the fraction part for single precision is 23 bits. So 23 plus 8 is 31 plus is 1 bit, total 32 bits. And the actual number that can be represented in this format is minus 1 to the power s. S can be 0 or 1 depending on the sign of the mantissa. And then here you see in the fraction 23 bits, but there is a hidden 1 is also there, which is not represented in 23 bits. So you are getting one more bit here. So 1 plus fraction and then times 2 to the power exponent minus bias. Okay, so we are going to see how to represent the number, then we'll get the experience. And so if 1 plus fraction with this 23 bits of fraction, so it will be, the mantissa will be 1.111123 maximum, I'm saying. So it will be very close to 2. Okay, and if the fraction part is all 0, it is still 1. So mantissa will range from 1 to 2, equal to 1 and very close to 2, because instead of 23 bits, if you have 52 bits, then it will be more close to 2. Okay, so so this number representation always has a leading pre-binary point, 1 bit, so no need to represent it explicitly. It is a hidden bit, and significant is fraction with the 1 point something. An exponent excess representation, actual exponent plus bias, and for single precision bias is 127, and for double precision bias is 1023. In your previous slide you have seen usually the bias is 2 to the power e minus 1. E is the number of bits for representing the exponent, but here actually they are taking one less. Instead of 128 they are using 127, and for double precision they are using 1023 as bias. So this is the single precision number system with 32 bits, and this is the double precision number system with 64 bits. Sign bit part is the same. Here 8 bits of exponent, here 11 bits of exponent, here bias is 127, and the exponent can range from minus 126 to plus 127. And for double precision, the exponent ranges from minus 1022 to 1023, and here 23 bits of fraction, here 52 bits of fraction. And this double precision was came much later in 2008 when computers started using 64 bits of data width. Okay, some features about this number representation system: single precision 32-bit, double precision 64-bit, and the significant bits is 23 in the fraction part, plus 1 hidden, which is the before the fraction, and then significant ranges from 1 to very close to 2. This number is very close to 2, and exponent bit is 8, exponent bias is 127, and if you want to represent a 0, then exponent will be all 0 and fraction will be all 0. And the normal representation, that like exponent all 0, fraction not 0, this is not a normal representation. And for infinity plus minus, exponent will be 255, fraction will be 0. And for NaN, not a number, exponent 255 if not 0. And ordinary numbers, the exponent will be from 1 to 254, which is minus 126 to 127. And the minimum number that can be represented is 1.2 in decimal into 10 to the power minus 38, and maximum number that can be represented is 3.4 into 10 to the power 38. So that is a big range of number that can be represented with 32 bits of data word. And similarly for double precision, you can go through it. So this exponent, all zeros and all ones are reserved, that is not ordinarily used. So for smallest value, 7 zeros and 1, an actual exponent is minus 127, which is told in the previous table, previous slide, and fraction is this 1.0. So this is the minimum number and this is the largest value of the number, which you have seen in the previous slide. And similarly for double precision, okay. So why is the exponent is biased? So there must be a reason, no? It is not 2's complement number. It is again biased with excess 127. Why? For faster comparison, for sorting, etc., and allow integer comparison of floating point numbers. So when you are going to see, you have to do arithmetic where the numbers are in floating point. There you have to compare, no, in multiplication or for addition, you have to compare. So this comparison become easier with this excess number representation system. So here an example is shown. If you want to represent half means 0.5 in unbiased exponent, then it will look like this. Half means 0.5, right? And 0.5 in binary is 0.1. But your binary point should be 1. There should be a leading 1. So it is 1.0 to the power 2 to the power minus 1. And these all ones, 8 ones, is equivalent to minus 1. And so this is the exponent part, and 1.0, all zeros in the fraction part, in the unbiased system. And with biased system, if you add minus 1 plus 127, so it will become 126. This will be the representation. Similarly for 2. 2 means 2 to the power 1. So it is 1 0. In binary it is 1 0, right? So you have to shift the binary point. You have to make it 1.0 and then 2 to the power 1. So exponent is 1 and fraction is all 0. So if you are adding the bias, 1 plus 127 is 128 here, and the fraction part. So decimal to IEEE 754, how to convert them? The basic techniques are given here. Represent the decimal in the form of plus minus 1.xxx and then 2 to the power y, and fill in the fields. Remember biased exponent and implicit 1 mantissa. So with that, these numbers you can convert. You can convert all the solution is already given, but I will be solving one problem with you. And so the conversion can be both ways, decimal to IEEE 754 And if the number is given in 750, IEEE 754, how to convert it in decimal? The answer is given here, okay? But I will be solving one of them with you. Suppose you have a number minus 0.75. It is a decimal number. How do you represent it as a single precision number? IEEE 754 single precision number. So first decimal to binary, this is the binary conversion, minus 0.11. This zero point 1 is zero point 0.5 in decimal, and this one is 0.25. So this is from decimal to binary. Now you have to normalize the number. So that means you have to push the shift the binary point towards right, and this is a negative, so this is minus 1 to the power 1, then this becomes 1.1 and 2 to the power minus 1. Okay, now you have to add the exponent. This is the exponent, minus 1 plus 127 is 126. 126 in binary is this. And for double precision, you are adding 1023 as bias. So it is said this is the sign bit, then this is the exponent part, and this is the fraction part. Okay. Now the other way of conversion, if a number is given in IEEE 754 standard, what is the value in decimal? So we can see that the sign bit is 1. We can see the green color bits are for the exponent, and it is coming out to be 129. And now because this is bias was added here, now you will be minusing the bias part. So 129 minus 127 will be only 2. And this is the fraction part, so there will be 1 implied, so it is 1.01. so this is the number, minus 1 into 1.01 is 1.25 in decimal, and this is 2 square, which is minus 5. So hope you understood it, and if required, please pause the video and go through them again. And there are several examples were given in the previous slide. Please solve them yourself and write me in the comment section if you have any problem.